think we should start. So has the recording started? So just let me know once the recording has started, and I'll start. Okay. Um, yeah, just let me know if you can see my screen now. Can you see? Can everybody see my screen? Okay. Um, so I also want to write simultaneously, and so that is the only reason I currently have the unlicensed version of OneNote. But nonetheless, so according to the schedule, today we'll be discussing four key aspects in optimization. We'll start with Metropolis algorithm, and then this will set an inspiration for the simulated annealing. We then look at the advantages and disadvantages of simulated annealing by discussing some elementary aspects of two main algorithms used primarily, not primarily, heavily in artificial intelligence, which are hill climbing and random walks. Then we analyze the major disadvantage of simulated annealing, and which will then set motivation to study adiabatic quantum computation and eventually quantum annealing. The main motive of this meeting is not to understand all this theory in that much detail, even though I'll try my best to cover at least the basic concepts of these four topics. But I want you to start working on the D-Wave system as soon as you can, because the coding on D-Wave does not require the knowledge of all these topics that we're going to discuss today. But these topics will at least help us to understand what is going on behind the scenes on the D-Wave quantum computer. How are we getting the results from that quantum computer? So in that regards only, so this is part one of the meeting, and most probably we'll soon be having another meeting where we will discuss the live. We will have the live coding of all these four main algorithms that we are going to discuss today. And then in the third and the final part of the meeting, my plan is to get you familiarized with the D-Wave Ocean software development kit, as well as um, how to code some elementary problems on D-Wave and get the results on an actual backend. So there are a number of inspirations that have been drawn from physics and as well as in nature. So in statistical physics, generally, you have different microstates of a system. And then you always see that you have a system which is characterized by pressure, temperature. So all these are macroscopic quantities or thermodynamic quantities, which which statistical physicists calculate by studying the microstates of the system. So microstate is just uh, one of the possible configurations of the system, and the word configuration will become very clear when we will discuss the Ising model and especially the spins. But for now, just think as microstate as just one of the possibilities or one of the configurations of the system. And obviously, there can be different configurations of the system depending upon the total energy, which in turn is dependent on the temperature. And using these different microstates, one can then calculate the average thermodynamic quantities like pressure, temperature, etc. So to begin with, um, we are familiar with some phase transitions like in solid to liquid to gas. Similarly, there are some other phase transitions that happen when you have a material which is in a ferromagnetic state, and then it uh, gets converted to a paramagnetic state on increasing the temperature beyond a critical point, which we call the critical temperature. So, as you are probably familiar from class 12th physics, so you have a ferromagnetic system. I remember in the NCRT book, there is this image where they say that so you have basically domains, and in each domain, all the spins they are aligned in one direction, such that on an average there is no net magnetic moment. But when you apply a magnetic field, they try to align, and so that gives you a magnetic system, a magnetized system. But what happens in paramagnetic state is there is no net magnetic moment. So when you increase the temperature, so there are two forces at play here. There are thermal fluctuations, which are trying to de-align those spins, and then there are spin interactions, which we will discuss after this, that are trying to align the spin in the direction of the magnetic field. So there's a constant tussle between these two forces, or in general, because mostly in statistical physics we talk about free energy. So there's a tussle between the internal energy and the TDS term, or the entropy term. So as you increase the temperature to very, very high values, it's usually free energy, that the term has U minus TD, DU minus TDS. When you increase the temperature significantly, this is the term which dominates. So the basically this term dominates, and the system becomes more and more random. So since these terms dominate at high temperature, so what happens is you no longer have the possibility to align the spins in a common direction, and there is no net magnetic moment associated with that. So just remember this term temperature fluctuations, because this is from where we will draw inspiration for statistical annealing. But so this is a phase transition, because earlier you were in one phase, which is the ferromagnetic state, and then after some critical temperature, which we write as Tc, you are now in a paramagnetic state. So the phase of your system has changed. For example, nickel becomes paramagnetic beyond critical temperature, which is 627 Kelvin, which is high enough. It's not like it will become paramagnetic at room temperature. You need this value of temperature, and beyond this, nickel will have a paramagnetic state. So why are we talking about these phase transitions? Because studying these phase transitions help us to understand the fundamental processes that are happening at the most minute level. And how do we understand this? So there is a model to understand this, which is the Ising model, um, which I want to discuss after discussing some more properties of phase transitions. So there are two types of phase transitions. So there's a first order phase transition, and there's a second order phase transition. So ferromagnetic to paramagnetic jump is a second order phase transition. So a first order phase transition is when you have a discontinuity in the first derivative of the free energy. And if there is a discontinuity in the second derivative of the free energy, then you have a second order phase transition. And for this system, so just these formulae I've written for some clarity. You do not need to like go into the mathematics of them as to how they have come in the first place, but just um, I will talk about this. So this M is the magnetization, where and N is the number of spins in the system. So this average value of M divided by N is magnetization per spin. So I've not explained spin. So just imagine that we you have a lattice, you have these atoms, and each atom is effectively represented by a spin. So if it is pointing up, it is called spin up, and it is given a value +1. If it is pointing down, it is given a value -1. It is called a spin down. So um, so you have this possible configuration of the system where you are effectively having atoms as spins. So some of them are pointing up, some of them are pointing down. A ferromagnetic state will be when most of them are pointing in the same direction. And paramagnetic is on an average, they do not point in any direction. That is, their net magnetic moment is zero. So what happens in this phase transition, if you make a plot of average magnetization per spin, this is the plot that we see. So here there is some non-zero value, and immediately beyond critical temperature Tc, this value goes, the value of magnetization, average magnetization per spin goes to zero. So this is actually called an order parameter, because order parameters are usually studied in phase transitions or where there is supersymmetry breaking. So this order parameter, before for t less than tc, it has some non-zero value, and after t greater than tc, its value goes to zero. So studying these order parameters help us to realize as to where phase transitions are happening. Note that obviously somebody has calculated these critical temperatures. How were they calculated? They basically studied magnetization per spin and made these plots and found, so okay, so this is where a jump is happening. So this formula, basically, it's the first derivative of the free energy. And in the graph, you can see there is no discontinuity. So definitely this is not a first order phase transition, because the first order derivative of the free energy is not giving a discontinuity here. Now, interesting phenomena happen if we look at the magnetic susceptibility of the system and make a plot for that. So magnetic susceptibility of the system is just given by this. And when you substitute average magnetization, which is minus dou F by dou B, into here, you get a second order derivative. And when you make a plot of the susceptibility as a function of temperature, now you see there's a discontinuity. And that is why, because the second order derivative has a discontinuity, it's a second order phase transition. So um, I have shown these plots, but an interesting question is, obviously these are also calculated experimentally, but now our aim is not to do that. Our aim is to make some simulations. So how do we calculate these quantities numerically? Um, Remember, these are thermodynamic or macroscopic properties of the system. And obviously they fluctuate a little bit. And that is the only reason we are always interested in the average value, because these values fluctuate over temperature and over time. Um, um, yeah, okay. So, so how do we calculate these quantities? So in a ferromagnetic state, all these spins, they interact with each other. So we now need a model to, so we now need something to model these interactions, which is basically done by an Ising model. So in German, it's called Ising, but that's the proper pronunciation of the scientist. His story is actually very cool. He has lived for, I think, around 94 or 98 years. And then he was a German, I think he was so he was a German physicist, and then he moved to US. I don't remember which university he joined in US, but he basically solved the one-dimensional Ising model. And then came another physicist named Onsager. He solved the second two-dimensional Ising model, and so on. And the search for the solution for three-dimensional Ising model is on the route. And so, like I've mentioned very briefly, that you have a system or a lattice where you have these atoms. You're representing all these atoms by a spin. So either they can have spin up or spin down. Here I have shown a 3D Ising model, and assume that there are n spins in the system. So how do we write the Hamiltonian for this system? This is, remember, we are trying to model our ferromagnetic state where there are interactions between spins. Um, so this is the Hamiltonian that was proposed by Ising, but originally it was for one dimension. Later on, obviously, a lot of work has been done, but the name is stuck. Like It's not like since Onsager solved the 2D easing model, so the name is not Onsager model. So for all these models, name has been stuck with easing, and different physicists have given different solutions to different areas, different actually parameterizations of this model. But the name is easing model for all those different parameterizations as well. So this is the standard one that he proposed. And so sigma I, sigma j are the spins in your system, which can take values 1 and minus 1. In JIJs, so these are the interactions between the ith and the jth spin. So these are actually called sites. So we call them sites. So each site, there is a spin. So assume two sites, ith and jth site, and you have, let's say, either all both pointing in the same direction or pointing in the opposite direction. So you have this configuration of the system. Remember the word configuration that I mentioned earlier. So you have one possible configuration where some spins are pointing up, some spins are pointing down. As we increase the temperature, these spins, the temperature fluctuations actually flips some of those spins, and as a result you get a different configuration or a different microstate. Like the proper terminology is a microstate of the system. So what is the purpose of doing all this? Our goal is to find a configuration of the system which basically accounts for the lowest energy of the entire system. And so what will be the lowest energy of this system? This is the Ising Hamiltonian, and that will help us to determine the lowest energy of the system. For simplicity, we are going to make some assumptions because otherwise the visualization will become fairly complicated. We assume that all these interactions between ith and jth spin, they are constant, and we just denote that by j. So that j comes outside here, and you basically have summation of sigma I sigma j. So the first assumption is that the interaction between each pair of spins is constant. Secondly, it is an isotropic system, which means basically if here you have an interaction j in this direction, and in this direction as well you have an interaction j. So there's an isotropy in the system. Third major assumption is that only nearest neighbor interactions, like we are only going to assume right now nearest neighbor interactions. That is, this spin can only interact with this spin, or this spin, or this spin, and so on. But this spin cannot interact with this spin. So the only interactions we are going to allow in this system for the sake of simplicity and without any loss of generality, that only nearest neighbor interactions are taken. So as a result, for all those spins, not at the edges or at the corners, or let's say inside, the coordination number is going to be 6. So here I have drawn one such possible configuration of a spin and its 6 nearest neighbors. So you can assume for some spin inside the middle, so, or like a body centered spin exactly at the center of this lattice. So you have this spin and there are its 6 nearest neighbors. So 4 of them are in its plane, 1, 2, 3, 4, and 2 of them are along the line perpendicular to the screen. So these two. And let's calculate how the interaction is going to look. Now, if both the spins, just keep this in mind, we are taking a slight detour as to see how energy, like what is the relation between the direction of the spins and the total energy. For simplicity, currently assume you only have 2 spins. So either they are pointing up or they are pointing down. So they are present at ith and jth sites, sigma I, sigma j, sigma I, sigma j. So if they are both pointing down, we know we will assign them values -1, -1. You multiply them, you get value 1, but then there's also minus j outside. So as a result, these two spins pointing down have a total energy of minus j. Now, if they're pointing up, you have value plus 1, but then is also minus j outside. So automatically, if they're pointing up or they're pointing down, their total energy is minus j. And similarly, you can see that if they are not pointing in the same direction, the total energy is j. So our goal is to minimize the energy of the system. So that will mean that all these spins either align up or basically in the same direction. So either they try to be up or they try to be down. Note that you may have wondered, like, why did we introduce this minus sign here in the first place? Because we are discussing ferromagnetic state and we want the spins to be in the same direction. That is, this minus sign basically ensures um, that the overall energy of the system goes down if you like if the spins are in the same aligned in the same direction. So for this possible subset of a configuration, you have all in the same direction. So each pair of spins, like with this central spin that we are looking at, will have minus j, minus j, minus j, minus j, minus j, minus j. So a total of minus 6j. Yeah, do not confuse this with joules. J is a constant. Probably should have taken some another constant. Um, and it's not even fair to say it's joules. It depends on a system a lot. It can be anything. Um, for the purposes of this meeting, do not consider any units because now after this we will switch to computer science problems where we will be defining the same energy but don't have units for that. So just say, so it's just minus 6j where j is the coupling strength between each pair of spins. Now what we do is now flip this spin because temperature fluctuations are going to flip the spins. Now let's say it points down. So all those six neighbors, now they are anti-parallel with this green colored spin. So overall, now they have energy 6j. So if I have flipped a spin, we can see that the total energy change is 12 joules. E2 minus E1, that is 12 joules. Now, because of this spin flipping here, our overall energy of the system has increased. So technically, one would think that you should reject this state because um, after the flipping of the spin, if we had landed in a configuration where the energy dropped down from minus 6j to let's say minus 8j, and the total energy change will be minus 2j, which is good for us because we want to land in a system where the overall energy is minimized. So a naive solution would be that reject all those spin flips which increase the energy. But that would be extremely wrong. Like we cannot, so these are called bad states because they are increasing the energy of the system, but we cannot reject those states because remember, this is not just happening in this, like whatever changes we make here, they are going to affect the entire system because uh, once we flip this and we say the total energy has increased, so we do not flip this spin. But there could have been a case where flipping this spin and flipping another spin somewhere actually led to an overall decrease in energy. My point is, you cannot just look at one particular space in your entire search space and decide that, oh, okay, so whatever is happening here best will work for the entire search space, which we also call as global search or will work very well globally. So whatever is happening best locally doesn't necessarily mean that it is happening best at a global scale. So we need to, so that is the idea. Like my point is, if you flip the spin, no doubt that this particular subset of the entire configuration, the energy has uh, increased. But there can be a case where, let's say, when we look at this spin, now if we flip this down, now this could lead to an overall decrease of the energy. So we cannot outrightly reject those bad states. And this is where we introduce the notion of probabilistic modeling. Because if the energy of this system decreases, we accept the spin, we accept the spin flip with probability 1. But if we land up in a bad state, we do not reject it outrightly, we accept it with certain probability. What form that probability will take is what we are going to look at next. So this completes a very brief idea of Ising model. This is extensively used both on D-Wave quantum systems as well as gate-based uh, platforms like Qiskit, IonQ, etc. So it is important that you familiarize yourself with the notion of Ising model, which is nothing but to model the interactions between the spins. Now try to draw some analogies here. These spins, they're binary variables because they're taking only two values. So later on, when we are looking at some problems, so you model your problem in this Hamiltonian form, where obviously those interactions between the spins will no longer be constant. So you model your problem statement into these constants. And then you try to look at an optimal configuration of the system, which is basically you assign these spins +1, -1, +1, -1, and so on. You calculate the energy. Then this is what we are doing here. The whole idea of flipping the spin is exactly we are trying to reach a state of minimum energy. And any problem statement that you will look at D-Wave or any other platform is to find an assignment of these spins. So your solution lies in the assignments of these spins, such that that particular assignment should correspond to the lowest energy eigenvalue of this Hamiltonian operator. Like that is the key idea here. Mm, that is why I'm discussing these spin flips. So this is just a sub-module of this main algorithm where we have to calculate the lowest energy solution and the corresponding spin assignment, or in quantum mechanics terms, or sorry, in linear algebra terms, the corresponding eigenfunction. Lowest energy eigenvalue and the corresponding eigenfunction. That is how you should draw the analogy here. Okay, so the delta E is 12 joules. Now we have seen, so the energy has increased. It's a bad state, we know, but we do not want to reject it outrightly. So I want to draw another analogy here, though we will discuss this later on. Why we cannot reject this state? My point is, let's say this is your energy landscape of the problem. You want to reach your global minima. You have a number of local minima. Now, if you reject this bad state outrightly, like let's say you were here, you reject this bad state, chances are you will be stuck here. However, if you had accepted it with certain probability, that is, so what this energy increase represent, that basically means climbing the hill, that your potential energy is now, you need some energy to climb this potential barrier. This is what 12, the increase in energy represents. Now if you do not accept this bad state, you will never end up in the global minimum. So most algorithms in general in computer science, when they started thinking of this problems in terms of energy landscape, would get stuck in these local minima very easily. We do not want that. We want to reach our global minima. That is the entire goal of this meeting, is to see as to look at the various algorithms that have come that help us reach these global minima. So you can have a problem statement where you want to maximize a cost function. So maximizing something is basically minus of minimizing. And that is the only reason we always look at the valleys, like our solutions are in the valleys, not on the mountain tops. So there's I would like you to think of one question here. Um, we see that the energy has increased. from minus 6 joule. Obviously, now the energy of the system after spin flip was 6 joules. An important thing to uh, like an important thing is where what is the source of this extra energy. I would like you to think about it, like where has this extra energy come from. Think about it that the entire system obviously cannot be in pure isolation, so it is in connection with the heat bath or a reservoir with which it is exchanging the energy. So whenever the energy increases, it takes the energy from the reservoir. In the vice versa case, it throws it out. But yeah, those of you who are familiar with statistical physics, it has to do with it's basically a canonical ensemble. But even if you're not familiar, just think that your system is obviously not in perfect isolation, and it is in connection with the reservoir with which it is exchanging the heat. So it is possible. My point is, we can definitely have these spin flips. You do not need to worry that energy conservation is violated here, which is not the case. So now we look at a Monte Carlo simulation algorithm. So what are Monte Carlo methods? They basically make use of the concept of randomization, or like if for those of you who are familiar with Python, you know that there is np dot random dot randn, and then you can generate these random numbers. Then like you if you have a uniform distribution, then you can generate it between 0 and 1. Obviously these are not pure random methods, these are pseudo random methods, but you have these random methods. So Monte Carlo methods make use of these random numbers, and because these algorithms are based on the idea of randomization. So if you have a good enough number of convergence steps, they actually help you reach the state of equilibria. So yeah, so let's just look at to how to design a Monte Carlo simulation for this particular um, method where we have to locate the minimum energy of the system. So I will come at the loops, like how the programming works. But before that, what you initially do, choose a random spin configuration of the entire system. So you have this 3D lattice here. Now initialize all these spins randomly using these random number generators. Some of them will be pointing up, pointing down. It does not even actually matter how you initialize a system. You can actually start with all the spins pointing up or all the spins pointing down. It is totally fine. But usually do it that like take a random configuration. Once you have done that, calculate the energy of the entire system. Remember, the energy we calculated here is just one of the subdomains of the entire system. You have to do it for all these spins. Remember, this summation I equal to 1 to n is for all the spins in the 3D lattice, and ij, this actually represents neighbors. So for every I, consider all the neighbors. So yeah, this when you expand the summation out, even for 5 spins along each direction, total of 125 spin, it is going to have a lot of terms. So once you assign a random configuration, calculate the energy of the system. Now choose a random spin, like we did. Like I told you, choose a spin. Like let's say, random number generator chose a spin which was at the center of the lattice. Now flip it. Remember, you have only flipped one spin, and then you calculate the energy of the entire system, which you basically um, have to be like in this case when you are having only one spin flip, just calculate that energy. And essentially, like my point is, earlier how we did it here, we knew that this is the spin here, and so we calculate the initial energy, then flip the spin and then calculate it. Now you have to calculate the energy of the entire system, because in the first step we are calculating the energy of the entire system. In the first step we have not chosen a spin, right? So you calculate these energies in steps 1 and step 1 and 2. Now calculate the difference delta E. Now obviously if delta E is less than 0, I will consider the case equal to 0. If it is less than 0, you accept it with probability 1, because you are going in a spin configuration or your problem assignment in such a way that the overall energy of the system is decreasing. Now, if it is equal to 0, which basically means that there has been no change in the energy configuration. So you can accept it with probability 1. So it's actually just jumping from one identical system to another identical system. So it doesn't matter. And if the energy of the system increases, that means it's a bad state. You do not want to reject it. So you accept it with certain probability, which is given by exponential of minus delta E by kBT, where kB is the Boltzmann constant, E is the temperature of the system, and delta is the energy difference. So I will discuss how this probability function works in simulated annealing. But for now, um, for those of you who have not taken statistical physics, this is a standard when this factor actually comes out when we are trying to maximize the entropy, and this is when we calculate the probability distribution, this factor actually comes up. But I will discuss all these factors, like what will happen if you increase the delta E, decrease T, how does probability change with those changes in these two parameters. But for now, you see that you accept the bad state with certain probability. What do I mean by accept here? So you calculate, so if delta E is greater than 0, you calculate this factor. You throw a random number generator again, let's say between 0 and 1. Let's say you got a value 0.8, and this value was 0.6. Now, it depends on the algorithm as well. Now, mostly in statistical physics, if this value is less than the random number generator, a random number thrown, then you accept the state. And basically, what I mean by accepting the state is you flip the spin. So what is this doing in the energy landscape? Because we accepted the state, obviously, this yeah, let me draw here. So you were somewhere here. Obviously, you had this potential barrier to cross. Now, when we say we accept the state, so basically we jump over the barrier. And you can see it is helping us explore our search space better. Otherwise, if we had not accepted this bad state, basically if we had not crossed this potential barrier, there is never a chance to end up in this global minima. So it's a randomized algorithm. This is not going to happen every time. So if, let's say, if this factor comes out to be zero point 0.06, so 6 out of 100 times it will cross. It will basically jump, but that is good enough. So because if it crosses, then the natural tendency of the algorithm is to go down. Now it's here. Again, we calculate the probability. Let's say um, it comes out to be 0.03. So 3 out of 100 times it will cross. And so you see, this is how we can land up in global minima. If we outrightly reject these bad states, we will most probably end up in the local minima. It also depends on where you start. For example, if you started here, you were lucky because now you're already in the global minima, but that's not always the case. You obviously run your algorithm multiple times um, and try to see how what's the behavior. So this is the main Monte Carlo simulations, basically steps, and you do it for. So remember, this was done for one spin. There are n spins in the system. So your inner loop is number of spins. So basically, for all, if there were, let's say, 125 spins, this entire loop will work for 125 times. Now, this is not enough because on an average, what it basically is doing is it is trying to uh, go and look at all these spins. But just for example, the inner loop, obviously it's randomized, so I cannot say that all these spins are covered, but just assume that um, we had a perfectly randomized algorithm, and so all these spins were covered. But that is just one iteration, right? The inner loop is just one it's covering the lattice just one time. It is not enough because it is randomized algorithm. Like I told you, if the probability here was 0.06, And if I only have one iteration, most probably it will again end up in the local minima. So we need to have more number of iterations. Let's say we had 100 iterations. So six out of those 100 out iterations, so basically outer loop, it will cross the energy barrier. That is why there's a need of another loop, which is the number of times we want to do the entire lattice. At this, we usually decide as to how many convergence steps we need. Usually, I think depends on the system a lot, but for 5 into 5 into 5 3D lattice, I think 1,000 convergence steps or even more. It obviously depends on your requirements. Should be good enough for this particular model. That is that is the motivation that I want to set, is why we need this outer loop, because inner loop will just traverse the entire lattice once. We need to do it more and more number of times, because if this probable if a rule is that we accept the state only if it is less than the random number thrown, this will not happen in just one iteration. We need more number of them to wiggle around these local minima. Okay, so what is the Metropolis algorithm, and what was this entire talk about all these thermodynamic quantities? So I'll just want to quickly say that here. So what we do is, remember, in this entire calculation, our temperature was fixed. But then how do we decide what value to take? Because this factor will ultimately have an effect on the probability. Because let's say this entire thing, including the minus sign, is very, very less, then chances are we will probably not jump the local minima. It is very important, as I will discuss this, as to how to choose this value of temperature in simulated annealing. It is very important. But to make these plots, like we saw for magnetization per spin and magnetic susceptibility as a function of temperature, so this is the Metropolis algorithm. What we do, um, so remember, this particular inner loop that basically covers all those lattice spins gives us one microstate at the when all the spins are covered. So you have one microstate. You calculate the energy EI after each inner loop. So if the outer loop runs 1,000 times, so you calculate the energies basically 1,000 times, and then you take the average of this energy. So this is the statistical physics formula, which is basically summation of EI, e raised to power minus EI by KBT divided by partition number. Just think of this as a probability distribution, some PI, some P of EI. Now it makes sense. Forget about the factor, but now it makes sense. This is how we take the averages. You have a probability distribution, and you want to calculate, sorry, and you want to calculate the energy of the system. So at each, okay, so for Metropolis algorithm, what we are doing here is keeping temperature T fixed. Let's say we set it at some high value. Let's say 100 degrees Celsius. Oh, it technically for nickel it was 627 Kelvin. So let's say we start around 100 degrees Celsius makes sense. We start around 100 degrees Celsius. We do these 1,000 times, and for each of that we calculate the energy EI. Then we calculate the average value that corresponds to 1 point. So this is plot of magnetization per spin. Just imagine if this is average energy. That is not the plot, but that will correspond to 1 point in this plot. Now you decrease the temperature. Oh, sorry. In this case, you increase the temperature from 100. Let's say you switch to 105 degrees Celsius. You do the same thing again. You calculate the average energy. This is how you make these plots. And when you will so I've given you the algorithm. You can make a code by yourself, and you will actually experience you will get this plot for magnetization. Magnetization is basically actually sum of these spins, and energy is given by the Ising Hamiltonian. You can obviously read more about this, not of very concern here, but I do want to point out one thing, that all these microstates, like having the energy ei, or all the configurations like having energy ei, do not carry the same weight now. Like it, you do not have the same probability to access all these microstates, because now if you see, probability is e raised to power minus ei by kbt divided by partition number, but forget about that. So it's basically a normalization constant. So just think of this as some c times e raised to power minus exponential of minus ei by kbt. Why do we need this normalization constant? Because we need to make sure the probability remains between 0 and 1. Otherwise, obviously, this factor, depending on kbt, can be greater than 1. So we need to make sure that is what this 1 by z is doing. It's the normalization factor. Now you see that um, you do not access all the microstates with the same probability. Even if keeping temperature T fixed, the probability now depends on the energy of the microstate. And you can see, if the energy of the microstate is low, keeping temperature fixed in the process, the probability to access that microstate also increases. So there is a inherent biasing, not inherent, like we have given this biasing to all these microstates. Now they do not carry the same weight. Think of these as weights. The states with lower energy have more weight, and thus more contribution to the probability, and thus they will end up contributing the most to the average energy. And um, so And the vice versa case is when the states having uh, the most energy will have the least contribution to the probability. And this is important because we cannot have a system or a probability distribution where we are sampling these microstates or accessing these microstates with equal probability. So this factor, and I will discuss the importance of these parameters delta E and T in simulated annealing, but we can right now see that these factors are helping us reach those global minima. This probability distribution is actually very effective. So this is how we calculate thermodynamic quantities. And technically, you might be thinking, since we do not know the information about these all these microstates, how do we calculate, like when we are coding, how do we calculate this normalization constant? Technically, what we do is calculate the summation ei and divide it by the number of steps, convergence steps, which was 1,000 that we took in our case. And then we do it for all temperatures, like changing the temperature. So basically, there is another outer loop too, which for this particular case increases the temperature from, like we discussed, 100 degrees Celsius to 647 Kelvin, even beyond that, 700 Kelvin for nickel. So because then that will include the transition point, and we will have this kind of behavior. Okay, so now we have seen that we do not reject those bad states, and we have a probabilistic algorithm in our hand. And so what is simulated annealing? Simulated because it's a simulation of something. That something is annealing. What is annealing? Annealing is used in metallurgy, where you want to have certain desired properties in your material. So how it's basically done? You heat the material, but then you cool it very, very slowly, and in order to get a crystalline or an ordered state, because it obviously depends a lot on what properties you want. But let's say, as you've studied in chemistry in class 11th, you have amorphous or crystalline solids. You want a crystalline solid. So how do you do that? You decrease the temperature very slowly, because if you decrease the temperature quickly or fastly, what basically happens is, um, the atoms, they quickly go to the places wherever they find space. So that leads to uh, a disorder on a global scale. So we do not want that, because when we have the crystalline solids, we know from third law of thermodynamics that the entropy is zero, because there is only one configuration of the system possible at that stage. That is the minimum energy state. So drawing inspiration from that, because we are always interested in minimum energy states or state solutions, we try to see as to whether we can simulate that principle that is widely found in our physical world to our problems at hand. So there are two popular algorithms: hill climbing and random walks. So they're basically trying to reach those minima, but they are not actually very effective in reaching those global minima. Hill climbing is directly based on steepest descent or a gradient descent. So let's say you start here, you look at all your neighbors and you try to see wherever your difference of the cost function becomes the steepest, and then you take your descent, and then you do that, and then it's basically so it's called hill climbing. If we were doing maximizing of our cost function, it's valley descent, because we are trying to reach the minimum. So because it will always look in the steepest direction, it will get stuck in the local minima. So um it's actually exploitation, because it exploits the local space in which it is present, but it does reach a solution. Important thing to note here is these local minima. So these are some of the lowest energy lying state solutions. It does reach one of the solution. I'm not saying that's the desired solution, but it does reach one of the local minima. So it exploits the local search or local space around it by moving in the direction of steepest descent. That's what hill climbing or valley descent is doing. I I think I did not explain what is a cost function. So cost function, or the objective function, is the function describing a problem statement which we are trying to minimize. In the easing model, it was the easing Hamiltonian, and we will soon discuss some problems. So where we will design some cost functions for the given problems. So just imagine it's a Hamiltonian function only for that problem, and you're trying to minimize that so as to find the solution of your system. So this is exploitation. And what does random walk do? Random walk is you are starting here and you randomly choose a neighbor, then you move there, and then again you choose a neighbor randomly, you move there, and so on. So as a result, if you are here, it can still randomly choose a neighbor which is present here and then move on. So it can go around the search space. So it is effectively exploring the search space better than the hill climbing method. But the only problem is we have no control over the random walk. Like, for example, um, how do we decide the number of convergence steps? Because it is moving randomly. For example, it actually reaches the global minima, but then moved again, and let's say it moved back. So we do not have a control as to where to stop it. But the advantage that we see with random walks is that it is exploring our entire search space effectively. And the advantage with the uh, valley descent or hill climbing algorithm is that it actually helps us reach the solution. I'm not saying it's the correct solution, but at least it helps us reach the local minima by always moving in the steepest descent. So there are advantages of both, and if we combine them, that is what we get: simulated annealing. So what is the algorithm for simulated annealing that combines the advantages of both these algorithms that are heavy? Like hill climbing is heavily used in artificial intelligence, and in other areas as well, because it's cheap. It's very cheap, because sometimes you're not interested in the best solution, you are sometimes interested in the lowest lying energy states. So hill climbing actually does not take any space, like any memory as such, and it's very cheap. So people use this algorithm. Obviously there are various modifications over this algorithm, but it's uh, very frequently used when you basically need solutions quickly. So what is the main idea behind simulated annealing? So you calculate again the same stuff that we looked at in the Metropolis algorithm, but there, if you remember, before we discussed the Metropolis algorithm, just when we were discussing the Monte Carlo simulation, the temperature T was kept fixed, and we had no idea as to from where, like what value to choose for this temperature T. So this is what we will explore in simulated annealing. Again, let's look at the energy landscape only. Suppose you start here and then you choose a random neighbor. You calculate the energy of the state, subtract it, you calculate delta E. You can have the same analogy with the spins. You are basically, what is happening? You have binary variables, some xi's. You are giving them assignments. In terms of spin, you are flipping those spins randomly. You're calculating the energy. You're trying to move um, in this energy landscape to a state where your solution lies. So you calculate delta E. Now, like I said, we do not want to reject our bad states. So we need to come up with a probability distribution function, which is dependent on delta E. And you'll see it's also dependent on temperature T as it was in this algorithm as well. Um, so computer scientists basically use a sigmoid function. It's very popularly used. So it's given by 1 plus e raised to power delta E by T. Let's look at this. Obviously, this ensures this probability, it basically ensures that the probability is between 0 and 1. So on the x-axis, we have delta E, and on the y-axis, we have the probability function that is given here. It can take values 0 to 1. I will discuss all these curves, but let's look at, if this is the probability function that we're going to use, let's look at some values. So say that our energy E1 is -6, like we saw when all those 6 spins were aligned parallelly to the central spin. The energy was -6J. We're assuming J equal to 1. So assume that E1 equal to -6. And also for our purposes now, we will set KB equal to 1. And like I said, we do not know how to look at temperature T. For now, fix temperature T as well. Like let's keep it 25. Now we look at the energy E2 of the system, calculate the change in energy and the corresponding value for probability. If we are starting from E1 equal to -6, if the energy increases, right? If the final energy is -3, delta E is positive, is we basically you substitute delta E here, temperature T equal 25 here, and you get probability value 0.47. Now take a case when the energy decreases from -6 to -12. So delta E is negative. So probability now increases 0.55, which makes sense because the energy of the system is decreasing and the probability to access that microstate or that configuration is increasing. Now, if you even reach a state where E2 is -30 and change in energy is -24, you end up with the probability 0.722. And if you keep on decreasing it further, you will reach minus 0.999, eventually 1. And if you keep on increasing the energy, you will end up with a probability of 0.0. But remember, everything, all this was kept at a fixed temperature T. So right now it makes sense that if the energy of the system decreases, the probability should increase. That's how we have defined this sigmoid function. Let's now look at the other way around, keeping delta E fixed and varying the temperature and finding the corresponding probability. Now assume that delta E equal to -6. Obviously, I also need to take the case where delta E is positive, but you will see it's very trivial by taking the case of where delta E is negative. But now we fix delta E equal to -6, and then we vary the temperature. Now, if you do on your calculator like take temperatures to 0.0001, you will see that the probability is almost close to 1. Now, if you increase the temperature from 1, 10, 25, 100, 10 raised to power 5, 10 raised to power 10, you see that the value of the probability keeps on decreasing until it reaches a fixed value, zero point 0.5. So even if you go beyond 10 raised to power 20, this value is hit. This is zero point 0.5 because this entire thing will essentially become 1. So the probability becomes zero point 0.5. Irrespective of delta E, your probability becomes zero point 0.5. So when temperature is very, very low, considering delta for the case delta E equal to negative, delta E is less than 0. When temperature is very, very low, the probability is 1. And when temperature is very, very high, probability is zero point 0.5. So basically you are stuck in this range. And very, very high temperature actually corresponds to random walk. Very, very low temperature corresponds to valley descent. Why? Because when temperature is very, very is close to 0, we see that the probability of accessing that energy at that state is close to 1. That is what is happening here basically. So when you reach your local minima, you are accessing that energy state with probability 1. Remember, in valley descent, we were not climbing up. We were not accepting the bad state. So we accepted this good state with probability 1. That is why at lower temperatures, you are basically using the properties of valley descent. And at higher temperatures, why does probability of zero point 0.5 correspond to random walk? Because what happened in random walk was you start somewhere, you randomly choose a neighbor. So either you go there or you not or you don't go there. So there's a probability of zero point 0.5. So at higher temperatures, you are um, in a probability of zero point 0.5. Now this will be our cooling schedule for annealing. Remember, in annealing, we cool things down because if we initially select the value of temperature T to be very high and then decrease our temperature very slowly or adiabatically, then what happens? So when the initial value of temperature is very high, so you are in a random walk regime. So basically, you are exploring all your search space like quickly. You are like moving around here and there. So that actually helps you to look at your search space judiciously. Now, as you cool down, basically, now you will end up in a regime of valley descent. Like now you will start looking at the steepest descent because random walk helped you to explore the search space, right? Now, now you have explored this search space. So as you decrease the temperature, you end up in the global minima. Now, this is a very bold statement. You might be thinking, how do I know that? Because random walk is like anywhere, like after at the end of the convergence, random walk was putting us here and then steepest descent landed up us in here. How do we know that I will end up in the global minima? And so there are a number of problems here. What is the initial value of temperature T that we initialize it to? Secondly, how do we know that we are in the correct solution? And thirdly, what is the cooling schedule that we need to take here? So these three things are actually also the major causes of concern for simulated annealing. So I would like to discuss one of the most popular cooling schedules that computer scientists take is they decrease the temperature as a by log of I, where I is the iteration number, like basically your outer loop or convergence loop, and a is some constant. This is the cooling schedule, not effective for every problem for sure, but this is the standard one that it takes. I think this is mostly used for traveling salesman problem. Traveling salesman problem. So now I want to discuss like the problem where I mentioned that, okay, so random walk helps us like to go everywhere, like, and as we decrease the temperature, then steepest descent will take over, and then we will end up in one of the minima. But is that minima global minima? So just look at this energy landscape. What is happening? This is a bad state, right? Like um, hill climbing If it started at here, hill climbing would just end up here. It will never cross this potential barrier because it does not accept the bad states. So the probability to accept a bad state in hill climbing is effectively zero. But we are not doing that. We are accepting this bad state with certain probability, which is given by the sigmoid function. So it's actually the thermal fluctuations which are helping us cross these energy barriers. Now, obviously, we can see that this energy barrier and this energy barrier is obviously very difficult to climb. Now, if we end up here, right? If we end up here, there is no way we can climb back up. I will tell this. I'll explain this with another values that I have taken here. If delta E is positive, remember when I say I have to climb up, climbing up means delta E is positive. Let's say if delta E equal to 6, we only took the values where delta E was negative. But now consider the case where delta E is positive and you are at the close of your algorithm where the temperature is almost close to zero. Now, if you take temperature equal to 0.01, you do this on a calculator, you will get the probability of 10 raised to power minus 260, which is effectively zero. That means you will not accept the state because this value is very, very zero, or very, very close to zero. There is no chance to access this microstate. So my point is, if you are in the global minima, this energy barrier is definitely very high. To cross them, this energy barrier, there's a very, obviously the probability is not zero. There's a very slight chance that it will cross back up. The thermal fluctuations will actually move our solution from the global minima to one of the local minima. But consider the opposite case. When we are in the local minima, the probability to climb this barrier is definitely higher to climb this barrier. So since the probability is high, thermal fluctuations will land up at the top of the hill, right? And afterwards, steepest descent will take over, and wherever the steepest descent is here, it will end up in the global minima. Obviously, this does not happen. It depends a lot on how you cool, because if the cooling was sudden, right? Let's say you start here and then the cooling is very sudden. You have hit T equal to 0 Kelvin. T equal to 0 Kelvin is basically the stopping criteria for the loop. Like this is where you basically stop. You will end up here. So cooling schedule matters a lot. When I say that, it also means all this information that we have seen, we are looking at the energy landscapes right now. We do not have the information of the energy landscapes a priori. So, to determine these cooling schedules properly for a problem, we need to have some information about the energy landscape a priori, which is not possible. And this is one of the major drawbacks of simulated annealing, that we because if we know the energy landscape, I can accordingly like give my cooling schedule, and that will effectively help me reach the global minima. But that is not the case always. So this is the major drawback, and this sets us a motivation to discuss quantum annealing. And another major drawback is this these thermal fluctuations. Obviously, they have certain probability associated with them, but if the energy barriers are too high to cross, let's say it's like something like this, we want to reach here. Now, we have already seen even for delta E equal to 6, and let's say if we are very close to the stopping criteria, there is no way it will cross this potential value. It is too high. So simulated annealing does not always ensure that we end up in the correct solution. But if you run the algorithm several times and you have an appropriate cooling schedule and a good stopping criteria, um, many NP hard problems or NP complete problems rather have been solved by simulated annealing. And so this is the sigmoid function that computer scientists use. We have just seen in Metropolis algorithm, even this will work the same. Physicists use this kind of probability distribution. C is a normalization constant, the same theory that we have discussed. And if you tabulate these values for using these, you will get similar results and similar behaviors. So this ends up our discussion on simulated annealing. Now I quickly want to discuss with you as to how we designed cost functions and like for the D-wave quantum computer, and then I will like to switch to quantum annealing. So there's a vertex cover problem in computer science. So you have an undirected graph G consisting of vertices V and edges E. This is yeah, forget about this right now. This is just an instance for the vertex cover problem that I've drawn here. You have an undirected graph G having vertices V and edges E. You want to determine a subset of V, which is V prime, such that it will contain a subset of the vertices. What is the criteria for the set? That for every edge, at least one of the two vertices is in V prime. That means for every edge connecting a pair of vertices, at least one of the two, either one or two or both of them, they are in V prime. This is the first. This we actually call it as constraint. This is the first constraint. And second constraint is that the size of the set V prime should be minimum. Everything will become clear from this example. Okay, so these are two constraints for the vertex cover. Forget about the minimum size vertex cover. Only consider this constraint, which states that for every edge, at least one of the two vertices is in V prime. So if that is the case, let's write V prime. A naive answer will be include all of them, because let's start with this edge. At least one of the two have to be in B prime, so include both of them. So 1 and 2 are both included. Because 2 is already included, it covers this edge, and 1 is included, it covers this edge. But there is no criteria of minimum size right now. I can also include 3, and because 1 was already covered, so for this edge this is also covered, but include 4 nonetheless. So naive solution will be this, where V prime is basically equal to V, which is of no interest to us. Now we impose an additional constraint that we want the size of the vertex cover to be minimum. Now can we look at some interesting solutions or not? So you have one, vertex 2, 3, and vertex 4. So let's start with this edge. Let's include 4. So if you include 4 in V prime, this edge is covered. The constraint is at least one of the two vertices have to be V prime. This edge is covered. Now we have to cover 3 more edges. Let's color one as well. Color by color, I mean include it in vertex cover, which is denoted by V prime. Now 4 and 1 are included in V prime. Now this automatically covers this edge as well as this edge, but this edge is not covered, which we can cover by including either 2 or 3 in V prime. This gives us a size of 3. Can we do better than this? We can. Actually, we have 1, let me draw this again, 2, 3, and then 4. Start with 1 now. Include this in the vertex cover. 1. This covers this edge, and this edge. Now we only need to include this edge, which can be done by either including 2 or 3 in the vertex cover. So you see, there's actually, for those of you who are not familiar with this term, there's actually called a degree of a node, which is for the undirected graph is basically the number of edges that are actually going, or like um, that the node is common on all those edges. So right now the degree of 1 is 3. So obviously, uh, greedily, when one has to start uh, looking at nodes which have the most degree. Right now degree of 4, node 4 is just 1, degree of 3 is 2, degree of second node is again 2, but degree of 1 is 3, because it has maximum number of edges with it. So it makes sense, because if we include this in V prime, it will automatically cover all those edges. So it makes sense to look at uh, um, um, nodes which have higher degree. But this is a greedy approach, and there are several problems associated with it, which I do not want to go into now. But so right now we have two different solutions possible. Now we discussed all this theory about easing Hamiltonians and whatnot. How do we formulate our problem statement into those Hamiltonian forms that we saw? How do we do that? First, we always, when you will be designing problems for on the D-Wave quantum computer, first think of the variables in your problem statement. Variables are your vertices. Let them denote by xi's. So variables are your vertices. Like next, you think of what values these variables can take. Here we can have binary variables that xi's can take value either zero or one. These are the only two values. Zero will mean it is not in the vertex cover. One will mean it is in the vertex cover. And in computer science term, we also denote, like convert this into a graph coloring problem, where if you color a graph or color a node, it basically means it is in V prime. If you do not color it, it is not in the vertex cover. So first we looked at our variables, which are nodes. Then the values that they can take, which are binary. What two binary values they can take? They are basically 0 and 1. You can also have minus 1 and 1. Totally up to you. But then you have to design your Hamiltonian properly. Um, so this step is done. This step is done. Third is to write the Hamiltonian. So for this problem, like if you want to encode your solution as the lowest energy eigenvalue of this Hamiltonian, you have to write the Hamiltonian accordingly. So this is actually typically written as xi plus d times summation 1 minus xi 1 minus xj, where ij belongs to an edge, I belongs to vertices v. Forget about this term right now. Forget about it. Just think of this term. What is this doing? So this summation is over all the edges. And for every edge, I and j are the nodes connecting, or basically that edge connecting those two nodes. So for every such edge, you are making this sum. Now, does this satisfy the first constraint, which states that for every edge at least one of the two vertices has to be in B prime? Remember, we want to encode our solution as the lowest energy or the ground state of edge. So think of this is your ith node and your jth node. By node here I also mean a vertex. This is your edge. So if you color I. Let's say if you color I, by coloring I mean assigning value 1, which basically means set it's in vertex cover. If you do that, this will take value 1. Let's say you do not color the other one. So this will this will take value 0. So overall, this will have a contribution of 0. So right now it does not contribute to the energy. Similarly, if you also color the other node, it will again be 1 minus 1 does not matter, again 0. Now the problem is if you do not color any of them, if you do not color any of them, then this will have value 0, this will have value 0. So now you will have 1 minus 0, 1 minus 0. So overall, now you have a term D. So this basically increased your energy. So this is actually good because we are now like we have so this formulation that we have written here is actually helping us, because if we do not color one of the two vertices, then we are basically straying away from a problem statement of the vertex cover, and that increases our energy. So this like the first constraint is essentially satisfied with this term. But now one has to wonder, can just this be the total Hamiltonian for the entire problem statement, which basically includes both these two constraints? Actually, no. For example, for this for this particular instance only, uh, like I discussed, without the second constraint, which is that we need a minimum size vertex cover, naive solution would have been 1, 2, 3, 4, right? If we have to satisfy both the constraints, and let's say if we say that this is our solution, what will happen? All nodes are essentially colored, right? So as a result, for every edge, there will be no net contribution. So for every edge, there will be 0, 0, 0, 0. So the net solution that we're looking has zero energy. So technically one would say, okay, so this is also a solution. That is why we need some another term in the Hamiltonian, which will make sure of the second constraint, which is we need to have a minimum size vertex cover, which is ensured by the second term here. So here the summation is over all the nodes. So if a node is colored, xi will be 1. So this increases the energy. If a node is not colored, right, so this becomes 0. And as a result, there is no net contribution to the energy. So now you can see there is a constant battle between these two constraints as to which will dominate over the other. How will that battle be determined? So that has to be taken um, by giving an equality or inequality condition between these two constants. So basically, they will then tell as to what factor dominate over the other. Um, so let's just look at, I think because this will help us visualize a little better, 1, 2, 3, and then 4. So you have 1 and 2. Like we know that the optimal solution was 1 and then either including 2 or 3. So let's look, if this is the case, then we know that all the edges are covered, right? And then, so this basically, there will be no contribution from here. But since two nodes are colored, there will be an effective contribution of 2C. You have a contribution of 2C. We also denote it in terms of binary variables. So this is, let's say, node 1, 2, 3, and 4. So you have 16 different possibilities, right? 0, 0, 0, 1 up to 1, 1, 1, 1. Somewhere here will be 1, 1, 1, 0, 0. Yeah, I should written have 1, 0, 1, 0, and then somewhere 1, 1, 0, 0. Obviously, 1, 0, 1, 0, and 1, 1, 0, 0 are our solutions. One has to be colored at any cost, and then either you color 2 or color 3. These are the two solutions, right? So for these, the Hamiltonian will have energy 2C. But for if all are colored, obviously this will not have any contribution from here. But if all of them are colored, all these values of all the nodes will be 1, 1, 1, effectively 4C. Now it makes sense because this has actually increased their energy. So definitely as compared to these, we have made sure that we do not get this as the solution. But then how do we decide as to which factor should dominate over the other? Um, let's say we know that 1010 is a solution. Let's flip the spin, like we saw in easing. Let's flip the third one. Let's look at this energy. If What will this correspond to in terms of graph? 1, 2, 3, and 4. So one is colored and all the others are not colored. So this edge is covered, this edge is covered, this edge is covered, not this one. So this will actually give a factor of D, right? And since only one node is colored, we will also have C. This will correspond to C plus D. This has value 2C. Let's look at another case. We color one more, 1, 1, 1, 0, right? If we color one more, we will have 3C effectively because three nodes are colored. And we have colored 1, 2, and 3. So no contribution from D. So this will give 3C. Obviously, this is 1000 is not our solution, right? This is our solution. So we need that this energy be greater than this. We want that C plus D be greater than 2C, right? So this gives us the condition D is greater than C. Now, the way that I'm deriving this is very, very bad, because this is just what happening in one example, that too not very effective. So there are a number of ways in computer science where we determine these inequality or equality conditions on these constants. Technically, this is not how you program it. So um, so in programming, what we do, just take C outside. Just take, oh God. Just take C outside. It's not working. Okay. Take C outside. It does not matter because these are just constants. You get D by C. In D wave, you will see everywhere we have a Lagrange multiplier. For those of you who have done some um, entropy maximization in statistical mechanics, like this is how we usually write. We have an objective function, and then we have a constraint, and we write our objective function, like the main function, what we want to maximize or minimize, and the constraint comes in the gamma, like gamma times the constraint. This is usually called a Lagrange multiplier. So while programming, what we basically do is we try out some different values of gamma and try to see if we are getting correct solution or not. But we do not know if we are getting the correct solution. So we obviously do it a couple number of times to see if we are getting, like, uh, all these quantum algorithms are probabilistic. So basically you make a plot for all these 16 possibilities, right? 111 probability plots. And obviously 1010 and 1100 will have the maximum height of the probability. Like when you make a histogram, this is, oh God. And this is what you get. Essentially, you basically run the algorithm multiple times. And so this is how we design the cost functions. You can think about it more, that why D should be greater than C. I would like to make one statement that might give you some sort of better insight visually. As let's say, if you are in your correct solution, and if you divert from that correct solution, like basically you, like if you were in 1010, if you uncolor one of the vertices, which leads to an incorrect solution. So if you uncolor if you uncolor, there will be a loss of factor from here, and there will be an increase in factor here. So you want to make sure that this dominates over the other, and that is why D has to be greater than C. Now, another problem that you might think is, where is the, like, why can't this be equal to C? For this, I will really suggest that for all the 16 possibilities, you calculate the Hamiltonian. And using this example, you will find out, unfortunately, I can do this, or maybe I can send this later on, because I think it's already 8:30. But if you do that, you like write all these energies, and you will very easily find out that why the equality condition does not hold true. But remember, all of this we are seeing is for this particular graph. So to generalize it to any undirected graph, it's a slightly difficult, and you obviously do not want to go into it, because even while coding, like I said, you just take seek outside and you have this Lagrange multiplier, change this value multiple times, for like keeping gamma fixed, run the algorithm, let's say 50 times, get your probabilities. This is how you actually determine a good value of the Lagrange multiplier. This is the standard way that people use on D-Wave computers. In general, when you have a large data, so the problem actually comes when you have large data and you have multiple solutions, like when you have degeneracies in your Hamiltonian. Um, then it becomes difficult, and at that time, people have KKT conditions in computer science and various other methods to calculate uh, good enough values for the Lagrange multipliers to start with. Yeah, I'm so sorry for the. I don't know what's happening, but okay. So I don't think we have time to cover quantum Hamiltonians for VQE algorithm, but I would, in the remaining half an hour, I would like to quickly discuss adiabatic quantum computation and quantum annealing. Uh, And in the next session, I would like to I have a total of 20 to 25 questions for which I would like to it will be very good that we design some cost functions for those 25 problems and then try to see in the third and the ultimate meeting where we try to implement them on D-Wave. So in the next meeting, we will we saw for vertex cover, we will try to develop the cost functions for a couple of other problems, which are some which are far more trickier than vertex cover, and some which are very simple and work very well intuitively. So, what is adiabatic quantum computation, and what is the hype behind D-wave quantum computers? How is that different than the Qiskit or the INQ or the gate-based models? So, adiabatic quantum computation. So, I would like to make one statement is of analog nature, and gate-based models, they are of discrete nature. So, what happens is I just want to quickly like this. And so in gate-based models, you have some qubits, let's say, some initialization. Then you have gates, right? So you have unitaries, let's say U1, U2, U3, and so on. So after every stage, that is after every unitary, you get some value for the qubits. So this is where the discreteness comes. Like at every stage you have, like in quantum mechanics terms, you write your wave function like psi1, psi2, psi3, psi4, which is given by the tensor product of all these individual qubits. And so you are able to do that, and that is why the gate based models, they have a discrete nature. uh, Contrary to that, adiabatic quantum computation is analog nature. So what is adiabatic? it, there are processes which evolve very slowly. And when in the last century, when scientists were thinking about such processes, as to where there are changes happening at an infinitesimally smaller pace, uh, how do the properties of that system change, right? So that is usually associated with the word adiabatic. It basically means very slow change of the system. For example, um, um, at this point, for those of you who are familiar with quantum mechanics, I will highly suggest that you watch the Quantum Physics 3 by Zwieback, MIT Open Course, OCW. And there are two main lectures on adiabatic quantum computation. For those of you who want to look in the mathematics of it, he has very beautifully explained the concept of adiabatic theorem. I will only mention you the theorem and some basic geometry for that. But if you want to go into the physics of it, I will highly suggest that you watch his lectures. So he starts with this example of pendulum. So yeah, just to give that example, because that is a very beautiful example. So you have a pendulum, and let's say Dushyant is standing here playing with that pendulum. Um, and you have like there is a capability to vary the length of the pendulum. And if you vary the length of the pendulum, because then obviously if you vary the length, the time period varies, and effectively omega varies. Now you slowly increase the length, very slowly, like infinitesimally, like at a very smaller pace. And obviously, when I say that, it's obviously relative. Usually, when we say the change is very small, it has to do with the comparison of the time scale of the problem with the with some another time. Here, that will be the time period. If time scale of the problem is tau, then you have time period t. You obviously get some relation between them, which he has also explained. But the length is increased so slowly depending on this tau and capital T, this change, that effectively the total Hamilton, when you write the total Hamiltonian, for what will be total Hamiltonian? P square by 2m plus half m omega square x square. But now omega becomes a function of time. So Hamiltonian is now time dependent. So when you increase, or like when you slowly change the length, omega t also changes very slowly. And then h also changes very slowly. So this slow change is called adiabatic. And then he discusses about adiabatic invariance, and then you will get some classical adiabatic invariance and so on, which are not of relevance to us. But this is what the adiabatic term means. Now, what is the adiabatic theorem? So adiabatic theorem, yeah, okay, so probably take a new page. So adiabatic theorem states that if you start in the ground state of some prepared system, let's say this is your system that you have prepared and you have full information about, you know it's Hamiltonian, you can prepare its wave function, basically the state that we usually see in quantum computing. You know the all the information. You start in this system, and that too in the ground state of the system. And here is your problem state, problem system, HP. This is usually we write it as HI. So this you have full information about. This you only know the HP. You obviously want to calculate the ground state of this problem Hamiltonian. How do we do that? So you start in the ground state of an initially prepared system, and then you adiabatically change uh, the Hamiltonian such that adiabatically, like obviously you will have to set a time scale for this problem. It depends on the problem, but just imagine the changes very slowly. Like if the time period, let's say, is 1 second for that pendulum, but that change, the effective change is happening over 5 years, let's say. This is the comparison that we are trying to draw. The change is very slow. So when you do that, and you are starting in the ground state of this initially prepared system, and I will write the Hamiltonian for this entire process, you will end up in the ground state of the problem Hamiltonian. So we write the Hamiltonian of the entire system as h of t, 1 minus t by capital T, hi, plus t by capital T, hp. So at t equal to 0, this term vanishes. So basically you have hi. At t equal to capital T, this term vanishes, and at that time h is equal to hp. So at t equal to 0, h is equal to hi, and at the end of convergence, h is equal to hp. So if you start with the ground state of this, and as you increase the time t from 0 to capital T, you end up in your problem system and in the ground state if the change was extremely slow. That is, if t is varied extremely slowly. But this is actually very hopeful, because our main goal is to calculate the ground state of the problem Hamiltonian, and this actually helps us in a very good way, because this is a system that we can prepare. And like we can prepare the ground state of the system, we know the entire information, and this is actually helping us to land in the ground state or in the solution of our problem. The only trouble is the how do we decide this capital T, which I will really like to discuss in the next meeting. This is very troublesome as to how we decide this convergence time. And also, secondly, how do we know that we will end up in the ground state? We can also end up in the excited states of the problem Hamiltonian. So there is no guarantee. And why will that happen? Like theoretically, adiabatic theorem states that we will end up in the ground state. But because there are temperature fluctuations in your system, this is only an ideal theorem, right? Realistically, like I said, your system is interacting, and there will be temperature fluctuations and many other effects. and quantum fluctuations as well. This is the ground state. Let's say this is the excited state of your problem Hamiltonian, and this is the state of the HT. You are trying to reach this ground state, but because of temperature fluctuations, you can cross and end up in the excited state. But what happens is we are usually interested in low-lying energy solutions of our problem Hamiltonian. Usually, like when you have very big data set, it does not it does not damage that if we do not end up in the solution. Even if we are ending up in the next best solution, it is good enough for us. So only in that sense, and this does not happen every time, obviously, but there is always a possibility to cross this. And there's a term called spectral gap, which is the difference between the ground state and the first excited state. And that spectral gap actually determines the value of t. So there's a big derivation that I will really like to go through next time. But the main idea behind adiabatic quantum computation is just this. So you have a problem Hamiltonian, this you can design the ground state of a given system. If you slowly vary it to end up in the ground state, or let's say the low-lying energy states of the problem Hamiltonian. So people often uh, interchangeably use adiabatic quantum computation and quantum annealing, but quantum annealing is um, a meta heuristic. I will explain what a meta heuristic is. So it's a meta heuristic which is implemented in the native instruction set of an adiabatic quantum computer. So if this is the funda or the idea, quantum annealing is the algorithm to implement this. Actually, um, so this concludes adiabatic theorem. Now I want to. The only reason I've discussed this because when we will look at the Hamiltonian for quantum annealing, you will see various similarities with this form. So what is quantum annealing? We looked at some drawbacks of simulated annealing, like basically temperature fluctuations that are helping us to cross these energy barriers or to climb those hills. Um, but we saw that if these barriers are high enough, or if the cooling schedule is not chosen properly, we cannot reach the global minima. Um, and there, the parameter which we were changing was temperature T. Here also, in quantum annealing, we have a parameter which is called the tunneling coefficient, which we initially set to a very high value, and then we gradually decrease over time. Quantum annealing makes use of quantum tunneling, something which is not available to us in simulated annealing. So I will not go into the details of quantum tunneling, but as an introductory course on quantum mechanics usually deals with quantum tunneling very quickly. So it's so you know that you do not have the energy to cross this barrier. So classically, there is no chance to cross this barrier, right? But quantum mechanically, because these particles can be represented as a wave, when you calculate the probability density, the probability, you will find out that there is a non-zero probability to cross this energy barrier. So what happens is, like if you start here, like steepest descent lands you up here, and then quantum tunneling, instead of crossing that high energy barrier, actually helps you to wiggle directly. This will wiggle directly and fall. So that is the major advantage of quantum tunneling. You do not have to climb all these high energy barriers. It's just like there's a tunnel. You make a tunnel through here, and then you quickly move through here. This looks very fancy and very comfortable. It also has a lot of problems, but let me discuss the how do we how it's done physically. So you have your problem Hamiltonian. To add to it so this is actually a weighting factor or a tunneling coefficient weighting factor times this HD. HD is called the disordering Hamiltonian or the kinetic energy term, which basically introduces quantum fluctuations. So bear with me on this. I mentioned that like in simulated annealing, we start with a high value of temperature. We also start with a high value of tunneling coefficient. So initially, when this value is very high, then this factor dominates over the problem Hamiltonian. And this factor, like I said, HD is disordering term. So it basically induces quantum fluctuations into the system. So this is actually in your initial state is actually very similar to a random walk. When tau t is very very high, it's similar to a random walk because the fluctuations are significantly high. So you're exploring your search space effectively. So this term dominates. And that is what we want initially. We want to explore a search space effectively and then decrease the temperature like we saw in simulated annealing so that the probability to cross high energy barriers decreases and then valley descent or hill climbing take over. And uh, now we decrease this value of tunneling coefficient to a point where it becomes actually zero. And that stage, we just have the problem Hamiltonian. And in that case, that is equivalent to hill climbing or valley descent. So the analogy is very same. The only difference is we are not crossing the energy barrier, we are tunneling through. So um, so this term dominates when this tends to zero. The only major trouble with quantum annealing is it depends on the barrier width. If the barrier width is very high, the probability to cross also depends on number of factors also decreases. So quantum annealing is not very effective if you have, let's say, something of this sort. Something of this sort. So your barriers have high widths, then tunneling becomes difficult as such. But overall, quantum annealing, it we cannot say as of now whether quantum annealing is better than simulated annealing. In some applications, quantum annealing has worked at par with the simulated annealing. In some applications, and that too in very few cases, it has worked better than simulated annealing. People are still trying to explore. It is a very new research area, and people are still trying to explore whether this works better or not. The only main key point is that D wave. I've been mentioning D wave based in I think Burnaby, Canada. Yeah. So their quantum computer makes use of quantum annealer chips. So they make use of quantum annealer chips, which we will discuss next, like how are they made. Just a quick discussion on the hardware of the D-Wave. But um, adiabatic quantum computers, they have uh, less, like the problems that gate-based quantum computers have, they definitely, adiabatic quantum computers have a lesser magnitude of those problems, but then they have their additional problems. So it is difficult to say on both hardware and software side whether one is performing better than the other. And then there is another problem that most of the problems that you can solve on the D-Wave quantum computer have are either these optimization problems or some sampling problems. There's also a limited set of problems that you can do. The plus point is, or the catch is, there is more control over the qubits in this paradigm. So essentially, that is why when you see D-Wave is releasing, oh God, 1,000 qubit, and now it's not even 1,000, it's much more bigger. So do not get overwhelmed by that, or do not think that D-Wave is performing better. Realize that the problems that they are tackling right now, they are very limited in size as well as in domain. And comparison to that, gate-based model is universal. And the problem with gate-based model is then circuit depths, and then the increased complexity with the increase in circuit depth and increase in number of qubits, and there is lesser control over the qubits. So that is why they're not able to like give these 1,000 qubit quantum computers. So um, so both sides have their pluses and minuses, but I'll say adiabatic quantum computation is easy to learn. Like at least programming on D-Wave is far more easier than programming on Qiskit, because essentially what you need to do is just have this cost function. Then you need to map it to a graph based model, and then just give it to the system. That's it. You do not have to know any of the quantum annealing, how the backend is working. You do not have to know, and you are essentially done. It gives you the results. You can then manipulate the results, publish a paper. There's a very good paper. Yeah, so we are almost at the end of the talk, last 5 minutes. So there's a very good paper that recently came. I will discuss this in the next session. Is the nurse scheduling algorithm, very standard classical algorithm where you have nurses in a hospital, like they have their own demands. Like some nurse says that that nurse does not want to work 2 days in a row, so they have their demands, and you want to uh, basically assign a schedule so that at least each patient is catered to in the given time frame. So there are classical algorithms, but then you can obviously write a cost function based on the vertex cover problem. It will be very similar to what we discussed today. So based on that, we write a cost function, and then we then send it to D-Wave quantum computer. We get the results, and they published a paper. I'll send it on WhatsApp or Telegram. It's a Nature paper, and you will realize that. um, Publishing on D-Wave is slightly easy if you know the right kind of problem you want to work on. However, working in on gate-based models is difficult because many a times it is hard to come up with circuits. Like in variational quantum eigensolvers, which we will also discuss next. I wanted to discuss today. It is hard to come up with ansatz for the problem statement. So in general, performance drops down significantly a lot. But then the same kind of problem is not necessarily always feasible on a D-Wave quantum computer. There is a trade-off, and and I think um, after reading this paper, you will, I think, appreciate the importance of a D-Wave quantum computer a lot. I think this concludes our discussion for today. So any questions? I'll see in chat. Okay, so there are, did you say, Bhargav, if you are still there, can you, um, okay, so adiabatic quantum computation and quantum annealing, the, we saw the similarity in the Hamiltonians that we wrote. The only difference is adiabatic quantum computation is a technique, it's a process. Quantum annealing is an algorithm that one implements in the native instruction set. I will discuss what these three words mean: native instruction set of an adiabatic quantum computer. So there are software stacks of every quantum computer, and then there's an instruction set. So whatever you write, whatever you feed to the like for example on D-Wave quantum computer, obviously, like I mentioned, you write the cost function and then you map it to a graph-based model, but you cannot send it to a quantum annealer chip. So in the backend, you have these instructions which map it to the appropriate set that is required, and then that is sent to the actual chip. So there's an instruction set where the quantum annealing algorithm is implemented. This entire computation is called adiabatic quantum computation. Um, so what is the meaning of when I was discussing statistical physics, and I don't think I've anywhere used bracket notation, it's just the average value. Yeah, do not when you were discussing originally statistical physics, I like Ising model and phase transition from ferromagnetic to paramagnetic, that meant the average value. They were not operators. So there was no quantum mechanics involved there. Um, So when I started writing easing Hamiltonian, somewhere I mentioned psi. There it was basically ket. I don't think I've, let me check, maybe I'm wrong. I don't think I've anywhere mentioned while discussing some quantum mechanics expectation value of any operator. Not here. If you saw those less than equal to sign, they were mostly, they meant average. But okay, so this is all average. Mm, yeah, I don't think that I've, yeah, but maybe I'm wrong. I'm sorry for the confusion, but just assume whatever was mentioned was basically average. And what else? Um, we can discuss Koenig's theorem, but it might be slightly out of context here for this particular meeting. So, like, we do not want to dive more into the computer science of these algorithms. We can definitely do that in chat as well. I do not know if there is any more important question in the chat, but if you want to ask anything, like you feel free to ask. And in case if there is nothing, then maybe we can stop recording.